Welcome back. So, for this lecture, we're going to keep diving down the rabbit hole of series and parallel circuits. And what I'd like to do for this one is really try to differentiate between the two. I gave you an example in the last lecture, very rough example about, hey, you can think of when you think of a series circuit, remember everything's kind of connected to the same wire like Christmas lights. And then you have a parallel circuit where things aren't on the same wire, but there's different branches. And that's at a very high level the difference between them. But when we're trying to calculate specific variables, so remember we have voltage, we have amperage, and we have resistance. If we're trying to calculate what one is based off of information we're given about another, then there's some big differences between series and parallel. And that's what we're going to talk about now. So let's go. And again, we left off with page 47. We talked briefly about this little diagram right here. Now, we're going to be talking a little bit more about these example problems. So there's a couple here that we'll discuss, and there's some more on the following page. So that's where we're headed. And again, if we're following along in the PowerPoint, we're still really on this one. And if you notice up here, we're on 32 out of 33. So we're going to be sticking on this slide. It's very, very light. There's not a lot of info in here. So for that reason, let's go ahead and go here. So again, this is where we were just a moment ago, and you can see just, the basics between a series circuit and a parallel circuit. But like I mentioned, we don't really have much information outside of that. So what is the relationship between, let's say, resistors when added in series versus resistors when added in parallel? So that's kind of going to be the theme. So don't get too intimidated by all this. This is what one looks like for a series circuit. And again, this is the simplest method. If we're doing something like this, it gets a little bit more complicated with parallel circuits, but not terribly. So just bear with me. And you can see I have a couple of notes. And again, this is not in your textbook. This is something I found somewhere else. So it's a really good thing to commit to memory. I usually avoid trying to tell you simply to memorize stuff, but this is one of those situations where memorization might serve you well. And again, what you would be memorizing is basically, if you're looking for, let me get this, RT, which is total resistance, you would just add R1, R2, and R3. And again, on the diagram here, this is resistor 1, resistor 2, resistor 3. And when I say resistors, some circuits, they add these little devices simply to introduce resistance into the circuit. But when we talk about resistors, we can talk about them a little bit more broadly. And like a resistor can be a light bulb, for example. And in a case like a series circuit, let's say you have a light bulb right here that's a 60-watt bulb. And let's say you have a light bulb right here that's a 40-watt bulb. And then let's say you have a light bulb right here that's a 100-watt bulb. So we have three individual values, but what we want to know is what's the total resistance for that circuit. So we just add them up. And if I remember correctly, I said 60, 40, 100, and that should add up to 200. So the total resistance for this circuit would be 200. And like I said, it's additive. So as we add them, as resistors are added, the total resistance to the circuit increases. Now, the good thing here is we have a gimme, and that's amperage. If you notice, total amperage equals amperage 1, amperage 2, amperage 3. So, in other words, the current is the same at all points in a series circuit. So if you're given an amperage, you don't have to do any math with it in a series circuit. It just is what it is. So let's say it's 30 amps, then you would just simply use 30 amps. You don't have to do anything else with them because it's constant. Now, when we're talking about voltage in a series circuit will actually drop across each element. So if you think about it, I gave an example a little bit ago about how there's some different resistors, 60 watt, a 40 watt, and a 100 watt. In this case, the 100 watt would be drawing the most, so it's the biggest resistor. But when we're talking about voltage, remember we also used the analogy a couple videos ago about water. And, if the resistance goes up, then the water won't flow as much. So it's the same kind of thing when we're talking about a circuit. So if the resistance increases, whoops, this one's probably the highest one, then the voltage decreases. So for that reason, if we want the total voltage in the circuit, it's also additive. So if you're given values, you just add them up and go from there. Now, let's contrast that with parallel circuits. So I mentioned it's a little bit more complicated, and the reason I say that is because it has these different legs like that, where the electrical current can flow. So because there's different legs, we could have different currents in each one of them. And if you notice here, we have IT, which is total, and that's the total amount of amperage in the circuit at this point before it travels down a branch. As soon as it travels down a branch, then we get different values. So in this case, if we were given different values, we would simply add our amperages to get the total amperage. And you can see once it gets out of all the branches, it comes back to being IT again. So that's total. That's total amperage. Now this one they give me is voltage, which is great because if we're given a value or if we calculate a value, we don't have to do anything else with it. It just is what it is. It's constant across all of them. Now, the reason I say this one's a little bit trickier is because your eyes don't deceive you. We have fractions down here. So because of the relationship between resistance, voltage, and amperage in a parallel circuit, and you can go deep down the rabbit hole and understand that relationship using Ohm's law. But again, for the purposes of this lecture and the purposes of what we need to know, we're not actually building circuits or doing anything crazy like that. So that's why I say just go ahead and memorize it for now. So memorize these, little formulas. But like I said, resistance decreases as resistors are added. And then for that reason, it would be 1 over whatever the value is. And again, you just add those up, and then you get 1 over the total on this side. So let's see what that looks like. So if we're, again, differentiating between series circuit on the left and parallel circuit on the right, each of these problems as we go down, and again, these are right out of your textbook, but they're basically the same value. So if you look, 10 amps, 10 amps, 10 volts, 10 volts, they're the same exact values, but it shows you how you're going to approach it if you're given this with a series circuit, or a parallel circuit, and you can see parallel. So let's go down the line. And again, I wouldn't be intimidated by these. They're pretty straightforward. Like I mentioned, if you're looking at the series circuit right here, you can see amperage. What is the total current? Okay, so it's asking for current in a series circuit where 3 resistances, each supplied with 10 amps. So total current, which is IT, you know what we're going to do. And in this case, they just equal each other. We don't have to do a whole lot with them. So 10 equals 10 equals 10 equals 10. So whatever you're given, that's what it is. Now let's contrast that with parallel circuits. If you have 3 resistances, each supplied with 10 amps, then what do you do? So it's a little bit different, but you can see up here, you're just going to add them. So in this case, instead of 10 equals 10, it's 10 plus 10 plus 10, which gives you 30. So that's straightforward. Let's keep going. So again, for a series circuit, supplied with 3 resistances, what is the total voltage with 3 resistances, each supplied with 10 volts? So before obviously it's additive, but let's just double check. We can say, okay, here's what we're going to use. So we know we're going to add them up, and if they each have add, 10, 10, and 10, we get 30. Same question over here, but remember, this is our free pass. We don't have to do any math whatsoever. Whatever we're given, that's what it is. And again, 10 volts equals 10 volts equals 10 volts equals 10 volts. Let's go down the line once more. What is the total resistance of a series circuit with resistances of 2.5, 4.2, and 6.8? Let's go back up for a sec. So we're going to add. When we do that, put them all together, and you end up with 13.5 ohms. And if we look on the right, same question. But like I said, this is the one where it's a little bit wackier. We have our fractions, but that's okay. So if we're going through here, you're going to set up your formula accordingly. And this is exactly how I would do it. You can do stuff where you know, when you add and subtract fractions, you can get a common denominator and do it just like that. Or what I would do is grab a calculator and do 1 divided by 2.5, and that's what you get. Same here, same here. And then once you add them all up, you get this 0.785. And then they sort of, and this is directly out of your textbook, they sort of skipped a step because look, right now this is our original and it's being brought down, but then it changes and they don't really tell you what happened. So what we did, I can hopefully fill in the blank a little bit. So between here and here, they took 1 over RT, and just like we do in class, if you multiply both sides by the denominator, so we're going to multiply this side by RT, multiply this side by RT, and then what we end up with is, carried over here, 1 equals 0.785 seconds times RT. But we want to get, remember, we want RT by itself. So then the next step is, because this is multiplication, we're going to go ahead divide both sides by what, 0.785, like that. And then, sorry, it's very scribbly, but once you cross this out and this out, you're basically left with that right there. Get that mess out of there. And then once you're here, again, you simply divide that by that, and then you're ended up with your total resistance, just like that. So again, oh, a little ding on my wall back there. Sorry about that. But again, like I said, this isn't the part where I'm going to put some critical thinking questions in it just yet. What I want to do is, we went through just some step by step. So the next video that I have, we'll go ahead and work through how to actually calculate these. Each one of these, we're just solving for one variable, but in some cases, you're giving more information and have to solve for it like that. So we'll do that in the next one. And I'll see you then.